Today we want to continue looking at gradients in space. Here's one of the things that we want to think about with gradients. This is going to be a very crude approximation, but it's going to be effective when we start thinking about things in future. The gradient is a vector built with partial derivatives. The gradient is a vector built with partial derivatives. So we can think of the gradient as a type of derivative. We want to think of the gradient as a type of derivative. We're trying to generalize our concept of what's the derivative. It's this vector combination of partial derivatives of a function of multiple variables. It's got derivatives in it. We're thinking of it, it's going to occupy the space of the derivative. This raises the question, what do we do with derivatives? So since this is a derivative, so now we've got to think back to calculus, the big picture of calculus, and think, what is it that we do with these derivatives? One of the things that shows up is tangent stuff, local linearity. I may be thinking of this because that's where I'm at in Calc 1. This always happens when I have Calc 1 and Calc 3 in the same semester. They start lining up, and conspiracy theories abound. Tangent stuff is just, and local linearity is just a variation on rates of change. Rates of change is interchangeable with derivative. Once we see something is connected to the derivative, it pulls in all the stuff that we thought about in Calc 1, and that we use the derivative for. So let's see what's going on here. We have derivative stuff. I just brought up the concept of local linearity. Let's take a look at finding some tangent planes. This is something that we've done before, but it's going to change a little bit now. So let's do an old problem first. So let's do an example. Find the equation of the plane This problem is going to more closely mimic what's going on. This problem will more closely mimic what's going on when we first started learning about tangent lines back in Calc 1. What's noticeable about this problem is that we have the surface described as a function. So what's noticeable about this problem is that the surface is described with a function. The surface is being described with a function. This means that we can easily get our hands on derivatives, on partial derivatives, rates of change. So what do we need for, I've got x naught and y naught. I can use the function to find z naught. That would give us a location, and the partial derivatives will be our direction. That's all we need with a linear function, a location and a direction. So to get z naught, I'll just find f at x naught, y naught. So we get 4 minus 1 minus 2. Oh yeah, that one was in practice circle. 4 minus 1 is 3, minus 2 is equal to 1. So z naught is equal to 1. So now we have a point, a location. 1, negative 1, 1. Kind of boring, I went with ones, but it's 8 o'clock in the morning. I haven't finished my coffee yet, so I don't think I can do anything more complicated. For a linear function, we just need two things, a location and a direction. Here is our location. Now we also need a direction, and for that, we're going to find two directions, specifically because we're dealing with a function. So I'm going to find fx and then evaluate this at x naught, y naught. Scroll. So we can imagine this plane, it's tangent to this, well, it's kind of an elliptic paraboloid, but it's just 4, and then we're subtracting an ellipse that grows large. So it's like a circular paraboloid, although I squished it a little bit in one direction. So we can imagine a plane. Our z is going to be tilted down in the x direction, down in the x direction, and up in the y direction. So we can imagine where we are on this surface, on this hill. We tilted down in the x direction and up in the y direction. So from here, we have all the parts that we need. We have a location, we have our location. And we have our direction. And it's described with these two different slopes because we started with a function. So the tangent plane will be z is equal to z naught, so this is where we start, plus the change in x plus the change in y, or the change with respect to y, and the change with respect to x. There's our linear approximation of this surface near the point 1, 1, 1, negative 1, 1. And we've imagined this tangent plane with these two directions. I've imagined the flat plane, and I tilt it down in the x direction and up in the y direction. So we can imagine on our surface, we can imagine that plane tilted down in the x direction, up in the y direction. If I rolled this plane around to a different location, so here's at 1, 1. If I instead put, 1, negative 1. If I instead imagine the point at 0, 1, if I imagine what's going on above 0, 1, that would be no change in the x direction, all change in the y direction. Let's think about what this would look like. So the level surfaces, if I make this a constant, the level curves are going to be ellipses. So looking from the top down, if we think of the level curves as ellipses, the point that I picked is at 1, negative 1. So also imagine that this is one level curve. I keep saying surfaces. One level curve, and we get higher level curves as we get closer to the origin. So there at the origin is the top of the hill. Going further away, we're falling down the hill. So we can imagine if we want to draw a plane, here it's going to be tilted in the negative x direction and the positive y direction, because we've got to be tilted. It's going to be going up the hill this way. Compare that to, say, a level curve at where x is 0. There, the tangent plane is not going to be changing in the x direction. It's only going to be tilted in the y direction. If we think about another one up at the top here, where y is 0, it's not going to be changing in the y direction. It's only going to be tilted in the x direction. We'll use our imagination so I don't have to draw them. Mainly I want to see who will write so I don't have to draw them in the note. Always when we do a problem, the boxed answer is never the point of the problem. It's all the thinking that goes along with our answer. We want to always decide, or we always want to think about, does our answer make sense? Can we picture this? Especially if we're going to be in R3 where things are nice and comfortable. We also want to think about other forms of what's going on. Think about other forms of what's going on. This was the point slope form where we have a location and a direction, or two directions. We can rewrite this into a standard form. we can rewrite the standard form of this equation by putting everything on one side. So I'll have 2x minus 1 minus 4 y plus 1, and then I'll have z minus 1, so plus 1 times z minus 1 equals 0. We still see the same location. But in the standard form, the coefficients of x, y, and z are the components of a vector normal to the surface. So our direction here is described not in terms of two slopes, but one normal vector. Instead of describing with two tangents, we're describing with one normal vector. So previously we had described the direction with tangent. Here we're describing the direction with a normal, perpendicular to the tangent. Whereas before we were using tangents, which are perpendicular to the normal. Any questions? Is everybody okay? Let's look at a variation of this problem. Same question, but we're going to change one thing about how we pose the question. So we've got a variation in how we are describing our surface. It's an equation in 3 variables rather than a function in 3 variables. Now we're describing our surface with an equation rather than a function. We're describing the surface with an equation rather than a function. The problem here is that I picked the sphere because it's the three-dimensional version of a circle, and we know that we can't write this as one function. Now, we could do a workaround. We're all engineers here. We could do a workaround and just figure out which part of the function we want. Which part of this equation we can make a function out of just the part that we want. It looks like if we take the z is negative part, we could make a function. So we do want to make a note of that. Note. Notice that we've either x positive, y positive, but z is negative. So we've got lots of ways that we could write this as a function. We would probably try to solve for z. We know that if we solve for z, there'll be a plus minus square roots. Let's just take the minus one because clearly z is negative. This is not describing the entire surface. This is just describing that bottom half of the sphere. Z is usually an up and down, so it should be the bottom half of the sphere. We could also just go with x equals the positive square root or y equals the positive square root if we wanted to be really different. But thinking as engineers, we could be practical. Let's make this an old problem. If the point of the exercise was to get at the equation of the tangent plane, that's probably what we would do. Make this an old problem. That's number 3 in the 3 great tricks of math. Just do an older problem. Do a problem that you already know. But we want to think about this differently. Because the point is not the tangent plane. The point is thinking about the gradient in space. So here's how our thinking is going to go. So our surface is described as an equation rather than a function. So here's what we're going to think of. We're going to think of this surface, this sphere, as a level curve of a function of 3 variables. We're going to think of this surface, this sphere, as a level curve, a level surface of a function of 3 variables. Rather than trying to force a function of 2 variables, we're just going to make a function of 3 variables, and this will be a level surface of that function of 3 variables. So our function will just be w f of x, y, and z is just going to be x squared plus y squared plus z squared. The sphere that we're concerned with is where w is equal to 14. That's what a level surface is. We just take the function and set it equal to some constant. Now the thinking goes like this. The gradient is going to be perpendicular to this level surface. The gradient will be perpendicular to the level surface, so it will be normal to the tangent plane. The gradient is perpendicular to the level surface. Because that's what gradients do. And so the gradient of f will be normal vector for the tangent plane. And we know the one way that we can build the equation of a plane is to take the components of the normal vector and make them coefficients of our variables. That direction combined with this point, 1, 2, 3, -3, will give us enough to make a linear equation, because all a linear equation wants is a location and a direction. That's why they're our favorite. They're simple. Location and direction, and that's it. So our gradient is going to be 2xi plus 2yj plus 2zk. Once again, I'm being lazy and taking it easy on myself because it's early. I don't think I do very much more complicated. I suppose I could have gone with an ellipsoid and just made one of these coefficients, but then I would have dropped it at some point. So that would have been dangerous. I want to evaluate this function or this gradient at the point that we care about. So it's going to be 2 times 1 . I don't know why I'm color coding still, but I can't stop now. 2 times 2 in the j direction plus 2 times -3 in the k direction. So here we're going to be using this gradient as the normal vector. So we've got the point 1, 2, 3, and our direction. So our direction is normal, and our location is the point 1, 2, 3 with a location and a direction. We can write a linear function. That's all a linear function is a location and a direction. So I'm going to take 2 times x minus 1 plus 4 times y minus 2 minus 6 times z minus a -3 is 0. Oops. I didn't mean that for it to be like a hidden and then a reveal. I didn't scroll enough. One thing that we want to notice with this is the boxed answer that we would put on a quiz and or test, which means it is definitely not the end of the problem. Because we need to think about what was going on earlier. Up above, we had proposed that we could make a function by thinking about what the point is, and then finding some partial derivatives of z with respect to x and y. And then we should think about what that equation would look, what the equation would look like in its z equals form, in its function form. So the point slope version of this would be z is equal to, let's see, I don't know if I'm going to be able to do this in one go, but we're going to try. No, I'm not. It's too early. Let's just rearrange this by solving for z. So we'll have a negative 6z plus 3. Move the x and y over, minus 2, x minus 1, minus 4, y minus 2. Divide out the negative 6 and then subtract 3. So z is equal to negative 3. That makes sense. In the function format, z naught should be negative 3. And we're going to increase by 1/3 when x differs from 1, and increase by 2/3 when y differs from 2. Now, if we wanted to verify this, we would just go back to our proposed function, z equals negative square root, take two partial derivatives, and then plug in the point, and check that dz dx evaluated at 1, 2 is 1/3. So we would want to check that that is consistent with what we had proposed before. That's what we would do if we wanted to think of this in terms of an old problem, in terms of the function. But the new thing today is that we want to look at this equation in 3 variables as a level curve of a function of 3 variables. Sorry, a level surface of a function of 3 variables. Any questions? How's everybody okay? Everybody's like, well, yeah, tangent line, got it. Derivatives. Yeah. I say things a lot over and over again because that's not how we typically describe lines. Usually we're a little more mercenary when we're in an algebra class because it's like all slope and point. But I like thinking more general terms because it's more useful going forward. Not just slope and point. The point is a location, the slope is a direction. That's what we need to make a linear function. The other thing that we don't bring up a lot when we're first studying linear functions is that that's everything about a linear function. That's why linear functions are so simple. That's why linear algebra is such an easy class. Everything is flat. It's just location and direction. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Oh, no roll.